Great. So thank you for the introduction and the invite. So we have another computation talk. So we're going to focus on the computational aspects of some of the things that we've been hearing about this morning and probably will be hearing tomorrow and the day after. This is a talk that I compiled from a bunch of papers from a research program that we've been running for a couple of years now. And especially this is work that I've been doing with, there you go. There you go. So with Pavel at Wasserstein Institute in Berlin and Sasha Gasnikov from FISTech. But yeah, so based on this audience, I'm assuming all of you are already experts in optimal transport. So I'm going to focus first on the first part of this title, on the decentralized, which I guess is going to be the nuanced part of this talk compared to the rest. So hopefully I'm going to spend a couple of minutes motivating the idea of decentralized computations, why this is important in real life when we are applying all the algorithms that we've been hearing about all day today, and then provide some computational complexity results on these particular problems. Great. So yeah, this is the plan for today. I'm going to first do a 101 distributed optimization review, so we are on board of what distributed optimization is. And then we're going to go how that connects to decentralized computations based on the super nice properties of primal-dual, primal duality of entropy-regularized optimal transport. And then we're going to see a couple of variations of this problem for which we can actually provide explicit convergence rate, convergence guarantees, and computational and sample complexity properties. Specifically, I'm going to focus on 3 applications. One of them is on semi-discrete barycenters. I'm going to explain what that is for those of you who do not know about it. And then I'm going to talk a little bit of quantization, which is more of an engineering problem. And then finally, a variation of optimal transport that we've been looking for about a year now that I think it's interesting, which is equitable optimal transport. But yeah, so let's start on the distributed optimization. Again, this is just a motivation slide. Many of the engineering systems that we work with these days, they don't come in a monolithic form. They usually come from connections or network of many individual systems. And here I'm just showing 4 classical examples of these. So one of them is like precision agriculture, where you have multiple sensors measuring properties of the soil, and they need somehow to cooperate and exchange information so they can execute optimal irrigation systems or optimal nutrient disposition on the agriculture. Again, we also have things like camera networks for securities, where instead of having sensors deep in the ground, we have cameras measuring things, and somehow they need to talk to each other in order to provide certain measurements or tracking properties of the scene. And you can think of these as security applications. And of course, we are all now on board with this huge scale ML when we have so much data that we cannot do computations locally, but we have somehow networks of servers working together in order to learn something. So this is the sort of the approach that we're going to see, or we're going to focus today, where we want to compute certain things from optimal transport, in this case, Wasserstein barycenters, and then the scale of the number of data points, the number of individual measures that we have is so large, or is generated in a distributed manner such that we need to do computations over a network, and that's going to be the main motivation. And of course, there's a couple of intersecting points in all these applications that I mentioned here. Of course, some commonalities among all of them is that all of these systems are described as connections of many units. I will call them agents in this talk. You can think of like a bunch of sensors talking to each other, of a bunch of people in a social network talking to each other, or a bunch of servers on a server system talking to each other, or a bunch of cameras talking to each other. So in a way, you have some form of local measurements and local computations. And this is what I call cyber and physical interactions. We're taking measurements from the real world, and we're doing some computations on them. And of course, we also have distributed storage and processing. And also, all these systems, they have a common set of challenges. So here I'm just mentioning a few, but the one that we're more interested today is this idea of decentralization, of can we design algorithms that can be executed in a decentralized manner? And don't worry, I'm going to be precise about what do I mean by that later on. And the idea of scalability is also important in these systems, which you can think of as scalability of how the complexity of your algorithm scales when the number of agents in this network grows. You can think of if you have 10 agents or 10 of these computers, 10 of these sensors is not the same as if you have hundreds of them or thousands of them. The idea of scalability is that we want to precisely characterize how the complexity or sample complexity of our algorithms scale with the number of agents in these networks. Of course, we're interested in optimality, and the question over there is pretty much obvious. Is this the best we can do with these algorithms? Can we have some lower bounds on performance for these methods? And of course, robustness and resiliency, which is can we still perform under failure? Right, and this is sort of like the object of study of distributed optimization in general. And you can see like here's just like a nice cartoon of what's going on. On the one hand, we have an optimization problem, and over there you can put your favorite optimization problem, right? So it's a linear regression, it's a logistic regression, it's your favorite neural network, whatever it is in the red ball. And the difference or the structural difference or structural assumption that we're gonna make in the distributed setting setup is that we also have this blue sphere here that we call the network of agents. And again, the main, let's say, the main differentiating assumption in this model is that we're gonna assume that each of these agents, each of these nodes in this network only has access to one of the functions in your objective function of the optimization problem that you want to solve, right? So if you look here, there you go. So the optimization problem that we're interested in, I define it as a sum over m functions. So my structural assumption is that I have a network of agents connected over a graph, right? So each of these circles is one of these agents. You can think of like a sensor or a camera or a drone or a server, you name it. And each one of them only has access to one of the functions, right? And you can think of if there is no if there is no blue circle here, of course, this is trivial, right? You pick your favorite method, you know what function class you're working with, and then you use gradient descent, right? That's pretty much how it goes. But now the question that we're going to ask is how can you perform or how can you design algorithms and provide convergence guarantees for methods in which the algorithm itself is executed over a network. And for example, this guy here only has access to one of the functions, Fi. From the practical point of view, you can think of let's say if you want to run gradient descent of this function, of course, if you have gradient descent of this function, you just like, take the gradient of the sum of the gradients and go for it. But in this case, this guy only has access to the gradient of one of the functions. So obviously, whatever this guy does needs to have some form of coordination aspect with all the neighbors such that you can converge to the minimizer. You don't want to converge to the minimizer of function 1. You want to converge to the minimizer of the sum of the functions. Right? Is this setup clear? That's the whole idea of distributed optimization. So this is the most basic example that you can think of distributed optimization. And what we have here, imagine, is that we have a network of agents. Again, this is how I'm drawing it here. Each of these dots is an agent. Again, a camera, a sensor, a person, a server. And in the simplest scenario, what I'm going to assume is that each of these agents has access to one number. Right? So this agent here knows one number, and this number is number 2. This guy here knows another number, and this number is number 5, etc. So each of these nodes has access to one single number, and the objective as a network is to compute the average of all these numbers. Right? That's the simplest case that we can think of. It's a distributed computation of an average. Right? Of course, if there is no network, there is no problem here. Just compute the average and that's it. But now the question is how to design an algorithm that is able to guarantee that after a couple of iterations, everybody in the network will have access to the average of all the numbers. And the structural assumption here is that we have this network that determines who can talk with whom. So not all the agents can talk to each other. So for example, it's impossible for this guy here that has the number 2 to know what this guy here has in memory, which is the number 5, right? So how can we design an algorithm that in a coordinated manner can compute the average of all these numbers? Again, I'm posing here the simplest problem that you can think of, right? Or what is equivalent, which again is just looking at a problem that looks like this. It's a sum of functions, but in this particular case, the functions is just the Euclidean distance, right? So this problem is equivalent of trying to solve this optimization problem, which is the sum of the Euclidean distances between xi's, which you can call this all of the individual numbers that each of the agents has in memory. You want to find one x that minimizes this, right? And here we're slowly going into the idea of a barycenter, right? You can already see it. This is what people call the Euclidean barycenter, aka the mean or the average, right? So this is say, okay, how can we compute the Euclidean barycenter in a distributed manner? And for this, of course, this is nothing new. This has been going over for like 50, 60 years. And the fundamental result under this scenario of computing averages in the Euclidean space, it's what we call the consensus algorithm, which looks something like this, right? And if you think about it, this is pretty much a trivial thing, right? So what I'm saying here is the agent I at iteration k plus 1 is going to be equal at some convex combination. I'm assuming that these are some weights of the information that is arriving from its neighbors, from the people that is connected to, right? So of course, if I is not connected to j, then aij is 0. Otherwise, you assign some weights, right? So this is a linear iteration. It's trivial. And the fundamental result there is that under very mild assumptions, so for example, that the graph is connected, right? So of course, if we want to compute the average of a bunch of numbers, the least we can assume is some form of connectivity in the graph. This can be relaxed. The graph is undirected and static. There's like more fancy versions of this, but let's stick with this for the moment. And the matrix A of the weights is doubly stochastic. Then we can have properties of this form, which is if you execute this algorithm, asymptotically, all of the agents I are going to converge to the average of the initial values, right? So what this is saying is if you execute this algorithm over a graph by repeated computations of averages, following the network structure, everybody agrees on the average of the initial values, right? And we call this a distributed computation because each agent only needs to talk to whoever is connected to, described by the topology of the graph in which they are embedded, right? They don't need any additional information. Yeah.
Excuse me, sir. So you don't have any assumption about some of the graphs that we have hubs, like you have more traffic in that, for example, agent of nodes, we say, we don't have such assignment.
Well, here the assumption is that the graph is connected, right? Right. I guess the topology, the specific topology of the graph will play a role in the convergence rate, and we're going to see that in a second. Again, just to have everybody on board, here I'm showing a network of 5 agents. Each one of them has a number. So how does this algorithm look like? Everybody sends the information to their neighbors, right? So agent 1 now has access to the information from 5 and to 2. So now it has 3 numbers in memory. Then they compute some form of averages on them, and then that's how they define the next iteration, right? So nothing new here. And of course, this is again for an average, but you can build up for more fancier and fancier version. What is the next thing after an average? A linear regression. So you can also do distributed computation of a linear regression. The only difference now is that, well, you have some generating model here, and now my cost function is some form of summation of the losses of the individual regressors, right? And then the assumption here is that each agent has access to pairs of H and B's based on this model, right? So what I'm trying to say here is that most of these distributed computation problems can be written as functions whose function class is a sum of individual functions where each of the agents has access to one of these functions. That's the overall setup.
Cesar, you don't impose any constraints on the bandwidth, let's say, of how much can be communicated?
No. Here I'm disregarding my wireless communication friends. I'm assuming perfect channels. I'm sending real numbers.
Can this be done? Like, can you work?
Yeah. There are versions that have quantization. When we go into the quantizations, I'm going to touch slightly here a little bit. But here I'm assuming this communication channel is perfect. I can transmit a vector of real numbers infinitely fast, right? Yes. But then the main property that we're going to work throughout again, comes from graph theory, and this is for the example that I was showing you before. This is a graph, and what I'm showing there, it's the graph Laplacian. All of you have seen this before. And the key property that we're going to use for our analysis is that the kernel of the graph Laplacian is what we call the consensus space, which is if you have a vector, this vector times the graph Laplacian is 0 if and only if all the entries in this vector are equal to each other. So when we're talking about consensus, what we really is like imposing a search space, which is specifically the kernel space of the graph Laplacian in which the nodes are embedded. Right? And then a little bit of analysis, right? So remember that this is the problem that we started with, right? We have a sum of functions. Then if we impose the condition that we want to be in the kernel of the graph Laplacian, what we can do now is separate these functions, right? Each of the individual functions has a different argument now, but then I'm imposing the condition that all of them should be equal to each other. So here I have done nothing, just rewriting the problem from one to the other. Right? But now what is interesting here is that we have a nice separable function subject to linear constraints. Right? And that as an optimizer, that makes us happy because we know how to solve those problems. So how do you solve a problem where you have a nice function subject to linear constraints? Well, you do some form of primal-dual analysis, and the type of approximate solutions that we're interested in is of this form: how close you are to optimality, and then how close you are to constraint satisfaction. And if you think of A as the graph Laplacian here, then what this second approximate definition is saying is how close you are to consensus, how close everybody is on agreeing a solution to this problem. Right? So how do you solve, again, this type of problems? You do primal-dual methods, right? So here what I'm doing is I'm rewriting our problem, right, in its dual formulation. And then I'm building my dual function here, phi, with respect to y, which is my dual variable. Right? Just, again, this is classical optimization theory. And then the interesting thing is I'm going to build up on the Danskin-Demyanov theorem, right? And what Danskin-Demyanov tells us is how can we take subgradients of functions that are defined as a maximization problem. And the interesting thing here is that Danskin-Demyanov tells us that the gradient of the dual function is just going to be this matrix A times this x star, and x star is just the argmax of my Lagrangian, right? So I have done, again, just massaging the problem here and there with classical primal-dual optimization theory. The interesting thing is, okay, what happens now? Remember that A is the graph Laplacian, so what happens now if we write this for an individual agent? What I have it here, right? So we have what we have now, it's a dual formulation of the problem subject with no constraints, and then we have a closed form solution of the gradient. So let's write gradient descent on the dual, right? And one of the interesting properties is that, for example, if your primal function is strongly convex, your dual function is smooth. There are certain conditions, and if your function is smooth, your dual function is strongly convex on a subspace of the kernel as well. And we also have the condition numbers. So basically, we can move from primal to dual without much of an issue. And then what happens when you do gradient descent on the dual? We have, again, gradient descent here. I'm just being fancy here and using Nesterov accelerated method, but you can ignore it if you don't like it. The interesting thing here is that the gradient step, this gradient step is defined by the graph Laplacian, right? So if I write down explicitly what's going on, what I end up being is that at every iteration, I just do an average of the information from my neighbors, but the information that I'm sharing is just the solution of the differential dual of my function, right? And then you can just execute gradient descent. But the important thing here is that I can execute this algorithm in a distributed manner, because if an agent I needs to execute this line of code, it only needs some information from the neighbors, J, and that's it. So this is essentially the same algorithm as the consensus algorithm that I show you at the beginning of just repeated averages of the information coming from the neighbors. Again, I haven't mentioned anything about optimal transport yet, but this is the key aspect I'm going to show you in a moment. However, if you have worked with primal-dual methods, one of the curses of these methods as well is that it hides away the fact that at every iteration, you need to solve this optimization problem, right? So the question is, okay, for what type of optimization problems is this possible, right? And this is where optimal transport comes in. It turns out that if you can solve this optimization problem in a closed form or super fast, let's say, with linear rates, we call these functions FIs to be dual-friendly. They have other names, but dual-friendly means that you can actually solve this problem super fast or even in closed form. And it turns out that the entropy-regularized Wasserstein distance is dual-friendly, right? So that means is that we have a closed form solution for this step, and this step is just communication from our neighbors. So then we have pretty much all the ingredients for a distributed computation of barycenters. I'm going to explain this. And again, here, I guess this answers your question. You pick your favorite network topology. And what I'm showing there is just the additional price that you have to pay for computational complexity. But as of now, I'm not worried about that. I'm just showing that there's dependency on the network topology. And we're going to see that in a second. Right, so now let's go into the method, right? If we have a function with linear constraints, we go into primal-dual. And if we just happens to have a function that is dual-friendly, then our algorithm is explicit. We have explicit solution for differential dual, and then the gradient step is just communication with our neighbors. And that is what happens exactly when the problem that we're trying to solve is the computation of discrete barycenter of discrete probability distributions. Right? So now the problem that I want you to imagine is the following. We have a network of agents again, but now the difference is that at every node, each agent is going to have a discrete probability distribution. And let's assume it's also finite, just to avoid unnecessary complexities, right? So we have a network of agents. Each node in the network has access to a discrete finite probability distribution. And the problem that we want to solve, instead of computing just the average of them, we want to compute the Wasserstein average of them, or in other words, the Wasserstein barycenter of them, right? Here I'm just writing it in a generic form. If we pick our favorite distance between probability distributions, you just solve this problem, but we are in this workshop, I'm assuming everybody's favorite distance is Wasserstein, right? So then how does this algorithm looks like when you pick your favorite distance, which is Wasserstein distances, right? And you see this a million times as well. So the Wasserstein distance between two probability distributions, discrete probability distributions being Q, are just classical definition, inner product subject to the transportation polytope. And then we're going to work with entropy-regularized versions, or let's say another fancier version. But it's the same, right? And again, you have seen this a million times. This is what we call the entropy-regularized Wasserstein distance. And of course, this is the transport plan, and this is your costs. So when we're talking about distributed computations, then this is the problem that we want to solve. Again, we have a network of agents. Each agent has access to one probability distribution. And then we want to solve this problem, which is we want to compute a probability distribution Q that lives in the simplex of dimension n, that minimizes the weighted distance or the weighted entropy-regularized Wasserstein distance between the distributions held by each of the agents and Q, right? So we want to find one single Q that minimizes this distance. If you have good imagination, you can change this W by Euclidean distance and P and Q to be numbers in the Euclidean space, and you go back to the average, right? The nasty part, of course, is that in the case of the Euclidean distance, everything has closed form, and then there is no computations to be done. In the Wasserstein case, then we need to solve actually an optimization problem to do this computation. Right. So far, so good? Is that clear, the problem? Great. So I'm not even writing the algorithm here because we have all the ingredients, right? And one of the ingredients that we have, of course, is Markov's result from 2016 that tells us that the entropy-regularized Wasserstein distance has a closed form differential dual, right? This is what I'm having here, right? So we have access to the dual of the entropy-regularized Wasserstein distance, and we have access to its gradient. So we have closed form for the gradients of the dual, And the gradient steps of the dual are also communication steps. So we have the algorithm. So basically, we can just plug and play all these results into the primal dual analysis for a linear convex function with linear constraints. We have access to the gradients. We have access to the communications. And the massaging that you do is exactly the same. So what we're going to assume is that we're going to try to solve this optimization problem where I assume we want equality or consensus among all of the Qs. And each of these Qis live in the simplex, and I want to minimize this problem. See, this is exactly the same as the Wasserstein barycenter problem. You do some massaging, you apply some primal dual theory. I'm not showing any proofs here, but this is the type of results that we can get under this analysis. Again, you have a network of agents. Each agent has access to one probability distribution Qi, and they run gradient descent on the dual of the entropy-regularized Wasserstein distance. And the type of cool results that we can have are something as follows. If you want some accuracy epsilon bigger than 0, and you have some bound on the gradient of the dual function, I'm going to talk about this in a second, we can provide explicit characterization of computational complexity. Explicit characterization is I can tell you exactly how many iterations do you need in order to guarantee that epsilon accuracy. And of course, this gamma here, it's the entropy regularization that we haven't talked about yet. And this lambda max on the lambda mean, you can think of this as the condition number of your graph Laplacian. And here's where the network topology plays a role, right? If you have a very nicely connected expander, this is going to be log n. And if you have like a pad graph, this is going to be like n squared, maybe. So the network topology, or how the agents are talking to each other, is hidden in this aspect here. And the type of guarantees that we can provide is that, of course, the duality gap is epsilon, and the consensus, the satisfaction of the constraints, in this case, the consensus constraint is of the order epsilon over r, and again, r is on the magnitude of the dual solution. Right.
Is this sharp in any sense? Do you know if...
Up to polylogarithmic terms, yes. Of course, this
polylogarithmic in epsilon?
In epsilon, yeah.
Okay. And one more question. Can you flip back to the previous slide for a second? So why, I just don't understand what this constraint means, that the Qs are equal.
Oh, yeah, because we want all of them to have the same solution, right? This is the problem. But remember that each agent has its own...
Oh, sorry, it's not the P's,
yeah.
the Qs.
The Qs, yeah.
Okay.
Maybe I switched the P's and the Qs in the notation. Yeah.
Okay, yeah. No.
Right. So yeah, the numbers, I'm not sure if 16 is sharp. Right now, you can...
That's not
in all of these bounds, usually this is like square root of 2, right? That's how it usually goes. But yeah, this one I'm not sure. But yeah, so, and then we can sharpen these bounds even more. We can provide explicit bounds on how R is based on like some analysis, and it will depend on the weights, and it will depend on the largest cost of your cost matrix, the infinity norm of your cost matrix, and on the minimum non-zero eigenvalue of your graph Laplacian, right? If you plug all these things, then we can have maybe a slightly more refined version of these bounds, which is by doing these primal dual accelerated versions of the entropy regularized Wasserstein problem, we can provide, here I think it should be O of all these, but we can provide explicit characterization of dependency on all of our parameters. The accuracy, how many agents do we have, the topology of the graph, the dimensions of our barycenter. Remember, this is the condition number of the graph, the accuracy of your solution, how many agents you have, the dimension of your distributions, your weights, and your cost function. I think you cannot be more explicit than this, right? So we have explicit dependency on all of our terms, and then we can guarantee, of course, primal dual gap and satisfaction of consensus constraints. We can also provide some arithmetic complexity because some of these things require matrix vector multiplications as well, but that's for the computer scientists in the room, right? So I'm not going to show the proof. I'm going to show proof by picture. Again, this is going back to the previous talk as well. This is like super classical scenario. You want to compute the Wasserstein barycenter of a bunch of discrete probability distributions, And just to make it more visual, what I'm going to assume is that the distributions that I'm working with are like these 2D representations of the MNIST dataset, right? So the support is just the pixels, and the gray value determines the mass at each of the pixels. I have a network of agents. Each of the agents has access to one of these numbers, and I want to compute the average of all these images, right? That's the problem. I was not able to embed the video, but I have it here, so give me 1 second. Okay. Okay, so what we're seeing here it's 100 samples of the number 2. I gave each of these samples to some person or some of these nodes in the graph. I connect them on an Erdos-Renyi graph. Why Erdos-Renyi? Why not, right? And then I run the algorithm. So this is the, well, it's not exactly the initialization. The initialization is something like this, right? So everybody starts with a different version of the number 2. We have closed form of the gradients. Communication is also closed form. And as the algorithm goes, they start talking to each other, start agreeing. They converge to the barycenter of these images, which is like a very nice sharp of the image of the number 2. And then consensus, everybody agrees on the same image, right? Let me show you another one, yes. Okay, just to show that it doesn't work only for 2, it also works for 3. Everybody converges to a nice barycenter of these images. And I have this one here with all the numbers as well, right? So everybody converges to a nice barycenter. Again, what is the meaning of a barycenter of an image? That's a different question, but let's say this is just like proof by picture that we're able to do this computation of averages of these objects, in this case, these 2D matrices, right, representing probability distributions.
And notice if you did that Wasserstein distance here, you didn't try other metrics?
What's that?
You didn't try any other metrics here?
Other metrics like?
I don't know, KS, or other metrics, I don't know.
Like Hellinger or, I mean, yeah, why not? But I think this goes back, right? So do we have a closed form solution of the dual? And I think that we have it for the optimal transport. I don't think we have it for others, right? So that's one of them. For K, you can use like KL divergence, right? But again, I don't think you have closed form solution, right? But then we will be in a different workshop on non-commutative Hellinger distances, right? This is the Wasserstein one, yeah.
So what closed form solution would you need for KL, for example? If you take Donskoy-Vardan, then you need the potential?
Well, we need a closed form of the differential dual, right? And I don't know.
Would it still be differential dual is still the right thing to look at if it's?
Yeah, because the formulation of F is the same. F is will be like the KL divergence between. But I can show you. Actually, I have a different paper on that. If you do KL divergence, you recover Bayes' theorem. But then I can send you that result. This is different. That will be for the Bayes' theorem workshop, right? But yeah, so that's sort of the idea there. And here is just a tiny variation of this problem. Again, the problem that I just showed you is you have a network of agents. Again, each agent has a discrete probability distribution, and you want to compute the average of all these, right? Sometimes the information that the agents have are continuous probability distributions. For example, like a generating model, right? And the difference is that they don't have access to the distribution itself. They have access to samples from that distribution. So the semi-discrete barycenter problem is as follows. You have a network of agents. Each agent has access to samples from a continuous distribution. And then you want to compute the discrete barycenter of all of those continuous distributions. That's what is called the semi-discrete. You have a bunch of continuous distributions, and you want to compute what is the discrete probability distributions that minimizes the Wasserstein distance between all of them, right? I'm going to define it here. So this is the definition. Slightly more nasty, but not really. So the entropy-regularized or the KL-regularized Wasserstein distance between two probability distributions, mu and nu, The difference is that mu is continuous and nu is discrete, right? So you can start seeing some similarities here. The first part is, of course, the cost, right? We have the integration with respect to the continuous distribution and the summation with respect to the discrete distribution. And then you also have to be careful about how you define the entropy regularization as well. Here is just the KL divergence with the uniform distribution here. And here the transportation polytope also changes because what you want is your marginals need to be defined properly. Marginal with respect to the continuous distribution and marginal with respect to the discrete distribution, right? And you might think of, okay, now the problem that I want to solve is the minimization of the sum of Wasserstein distances between a discrete probability distribution P, which is my optimization variable, and a bunch of continuous distributions mu sub I, right? And this looks way more nastier than it looks, but again, optimal transport is so nice and computationally cool that we have a very interesting property, like super cool property of optimal transport, entropy regularized optimal transport. You ask why do we do that? It's because we have properties like this, which is the dual function of the semi-discrete Wasserstein distance is an expectation with respect to the continuous probability distribution. And the gradient is also defined as an expectation, as you can imagine. And why do we like that? Well, because we all have done stochastic gradient descent. And stochastic gradient descent is specifically tailored to minimize functions defined as expectations. So what we're going to do now is we're going to do primal-dual analysis, but by taking stochastic gradient steps in the dual step, right? And this is the key slide here, right? The key slide is that when we're working with semi-discrete formulations of optimal transport, the dual is an expectation, right? And it's an expectation. You can just take samples from that continuous distribution Y, and then you can find approximate versions of your gradient. So you have unbiased estimators of your gradient, you're good to go, right? So that's the idea of this problem. Moreover, we have a bunch of properties. The dual of the entropy regularized is smooth. This doesn't happen if you don't have entropy regularization, right? And this comes all the way to the initial slides, right? So it's because this primal-dual relationship. Your function, the cost function of optimal transport is just convex, but once you add entropy regularization, it's strongly convex, so the dual is smooth, right? And moreover, we can have explicit forms for the smoothness constant, which depends on the maximum eigenvalue of the graph Laplacian and your entropy regularization. And here you can see why, right? So if your entropy regularization goes to 0, then you don't have smoothness, right? Also, not only that, but we can have unbiased estimators if you have M samples. So this is just what happens if you have M samples. Again, I'm not going to show you many details, but what I can tell you is you can just apply stochastic gradient descent on this dual function, and the type of results that we can provide are follows. We can give you exactly how many iterations do you need with dependency on the accuracy to the entropy regularization, the maximum eigenvalue of your graph Laplacian in order to guarantee a duality gap here and error on the consensus variable. Right? So again, the idea here is that the structure of optimal transport has all these nice properties once you add entropy regularization that allows you to take all the toolbooks that you have from optimization theory, primal-dual analysis, stochastic gradient methods to provide explicit non-asymptotic sample complexity bounds for your methods. Right? Again, proof by picture showing that everything goes to 0, but nothing much to see here. You can do it for discrete distributions that look like Gaussians. They're not exactly Gaussians, but they look like Gaussians. They work just fine as well. And I'm going to skip this one for a second. But yes, so now we're going to go into, let's say, a little bit of the engineering aspects of this, right? So as we see, all of these algorithms, the way they work is that you compute this closed form solution of the differential dual, for which we have it for optimal transport and semi-discrete optimal transport. And then you do a communication round with your neighbors, right? You average your current iterates with your neighbors. That's sort of like the two steps. Gradient step, communication step, right? That's what you do. But if the dimension of your distributions is very large, this communication step is inefficient from the engineering perspective, right? So if you're thinking about these images, they're not too big. I think MNIST is like 28 by 28, so not too much. But if your distributions, the support of your distributions is very large, you have to communicate this with your neighbors, and that might be very time-consuming, right? Or very, not time-consuming, but very energy-consuming, right? The communication aspects of these type of things are very energy inefficient. So how can we improve the communication efficiency of these computations? And this is where quantization appears, right? We don't want to send vectors of real numbers. We want to send some sparse versions of them, right? And this is probably too much text, but then again, going back to this original idea, right? The semi-discrete optimization problem, I just wrote it here again. The dual function of the semi-discrete optimal transport is an expectation. The gradient of that dual function is also an expectation. We can take samples from the random variable y, which is distributed according to mu, so we can have, let's say, estimates of this, empirical estimates of this function here, which is what I have here, right? So let's say I took M1 samples from that random variable y, so I can build a nice empirical estimator of my gradient, right? And so far, so good. But the interesting thing that we can exploit is that the gradients of the dual function here not only can be approximated like this, but the gradients live in the simplex. So the gradients themselves are probability distributions. So we can do another step of quantization in which we can just sample from those gradients. And if I want be clear here, right? So in the first step, we have an expectation. We take samples from y, and we get the empirical version of this guy here, right? But this gradient, this empirical gradient here, lives in the simplex. So I can take this as a discrete probability distribution and take samples from that distribution. And that will give us another step of quantization where we only need to send entries of this vector, right? And this is what I'm showing here. So after some analysis, what we can do is as follows, right? So first, you take M1 samples to get the estimate of your gradient. And then you take this gradient, because it lives in the simplex, you can take more samples or samples from that IID as well. And then your estimate of the gradient looks something like this, where M2 is the number of samples that you took from this probability distribution, and E is just the indicator function. So it's just a histogram of counts. So again, I'm exploiting the nice structure of the dual of this optimal transport distance to make it efficient even at the communication step. Because here, if you look at this, I just need to send a histogram of counts, so you only need log n bits for this communication. So what we're saying here is that this communication between agents is also very cheap. You only need log n bits, right? Moreover, you can continue analyzing. Of course, all of these quantized gradients are unbiased. And then we also have explicit forms for the second moment. So you can think of this as the standard deviation. So we can control with the number of samples at the first round of iteration, quantization, and number of samples at the second round of quantization, how big or how small do we want our standard deviations, right? But again, all of these are the auxiliary lemmas, because the only thing that we care is some bounded first and second order moments, and then we can run stochastic gradient descent, right? Again, we're here just building up the lemmas that allows us to apply stochastic gradient descent in all of these formulations. I'm going to skip this. And again, this one looks very nasty. I'm going to try to parse what is going on here, right? So the type of results that we can provide are as follows. So the first part is relatively easy. So we want to compute a probability of how far we are, or the probability of being epsilon away from optimality, right? So this one is easy. How far are we from optimality at iteration t with respect to this epsilon here? And I can tell you exactly how this epsilon looks like. The main result is that this constant C1, you can hide here, is polylogarithmic in t, in the number of iterations. And if you remember from your optimization theory, this AT grows linearly. So we got convergence, right? So we have in the numerator something that grows as logarithmically in t, and we have in the denominator something that grows linearly. So we have convergence here at the rate of log t over t, right? Again, this result is pretty much nothing new. It's just applying different variations of stochastic gradient method on the specific formulation of the entropy-regularized semi-discrete formulation of the optimal transport problem. And I'm going to, again, another proof by picture. There is no video here. The only difference when you do this extra sampling is that you see your estimates get a little bit blurry. Of course, you're taking just samples from these images. But you can see that after a couple of iterations, you still get nice results on the barycenter. And it works just as well for the Gaussian case. Here, x-axis is number of iterations. Y-axis is different values of the sampling, right? For example, the top one is what happens if you have just accelerated gradient method, and the second row is what happens if you're only taking one sample at a time of your distributions. Still very noisy, but you can see as the number of sample increases, you get closer and closer to the solution. Right. And then lastly, I'm going to present a variation of optimal transport that maybe is new for some of you. It's called equitable optimal transport. And now that you know, I mean, you've been hearing about optimal transport the whole day, I guess this will be kind of clear, and I just only need to show you this image, right? So here it looks, the cost looks like optimal transport cost that we've seen. The only difference now is that I define different costs, CK, for n agents, and different transport plans, XK, for each agent. So you can think of this as like the cost of the individual agent. And the constraints that I have is, first of all, I want the cost of all the agents to be equal to each other. And the marginal constraints are slightly different, because what I want is the sum of all the transportation costs to hold these two marginal constraints. So this is called the equitable optimal transport, because you're trying to solve an optimal transport problem, but what you care is not that everybody agrees on the transport plan. You want everybody agrees on the costs that they are incurring for their particular sub-transport plan that you have here, right? So you want the sum of the individual transport plans to have the marginal constraints, and you want the individual costs to be equal to each other. And this is formulations that they have. People are using a lot in machine learning these days for fairness, although that's a forbidden word these days. But if you want to do fair ML, this is the formulation that you want for your optimal transport problems as well. Again, proof by picture. It converges. It's a little bit wobbly, this one, but we showed that it converges at some point. And with this, I'm going to finish. Again, this has been a bunch of different results that I've been working with most of my collaborators in the past couple of years, focus explicitly on computations, right? So we have very nice formulations of optimal transport, so let's exploit all these cool properties that Wasserstein distances have to make it like computationally efficient and implementable on all of these distributed settings. Yeah, I'll start there. Thank you.